So I think we talked slightly about DP in the last session of brute force and recursion, when we were discussing about how to write brute force, and that in that chocolate breaking problem where we had to break the chocolates and get some rewards. In short, we talked about that we build some sort of recursion, and we note that okay, like some recursion is being called repeatedly, and the computation is being repeated a lot of number of times, and we need to store that value in order to return that value really fast, right? Like same function, same state is being called a lot of number of times, and we just need to return it then and there rather than calculating it again and again, right? So that's the whole idea of DP. There is no like new fancy idea that is going to come up in DP. Just now, from now on, the terminologies would be like, we would be taking terms and like taking notations in these sense that we will write something of this form, okay? And whatever we write in this is called state. You can think in terms of like these are the parameters of the recursion. Like what are the parameters that you keep in the recursive function? That is also something you can think it about in that sense. But these are something called states, okay? And what do we store is called, let's say, called the value of DP, okay? Value of DP. What are we storing? Okay. And the third thing is, like from one particular state, whatever state you keep, let's suppose we are keeping some sort of I comma x. Okay, this is some hypothetical state, I comma x. What all states this depend upon, or like from this state, which states can we go to, or maybe this states depends on which state, okay? Okay. So there might be two types of relation. Now we will call, let's say from I minus 1 comma some y, you could go to this I comma x, right? From this particular state, you could do some operation and go to this state, okay? This configuration. So so when you're thinking about DP or recursion, think in terms of configuration, that this is some system which has these and this as the configuration, and some sort of states are present, and from this state I can do some move and go to this state, okay? This is what you should be thinking when you're talking about DP. And from this state you can move do some move and go to the next state, okay? Now there are two styles of code that people follow in DP. I will talk about both very briefly. Now one is, when you have this particular state, people try to calculate this value using from where you can come into this particular part, right? This is one particular idea, that you construct the value of DP I comma x using the values from which you can come to this particular value, right? So this is one particular implementation idea. Another implementation idea would be one that is used in iterative one. So this you might have seen by now in a lot of times in recursive functions, that based on this, when you want to calculate the recursion for this, we sometimes call smaller recursions, like I minus 1 is a smaller version of the same problem, right? With some other states and some other states, right? Some others, like merging the results of these states give you the result for this state, right? So this side of the diagram would be like more like recursive, right? This is recursive part of the flow. Now if you try to code DP in iterative style, we can use both, but this is also possible. That's why I wanted to like quickly go through this, that you know the value of DP of I comma x, so just add its value, or like whatever like contribution it will be to the next value, just add it to the other next state that it will go to, right? Like I plus 1 comma x. Let's say I plus 1 comma z is going to need this value. Let's say I plus 1 comma z is sum of two different states, right? So when you come to this state itself, just add its value to this. When you come to this state, add its value to this. So when you come to this state, you already have the value built in at this state. So then you will add this value to the next, whichever state this is needed, right? So this kind of like implementation is also possible. However, for now, we will mostly follow the recursive one because it's much easier to understand, okay? And the main thing is you should build this one first than this one, because like even if you like build this one, still this might remain lacking and you might face problems in some problems, okay? So some questions. So that's why this is must, and this is something you should learn after learning recursive, because some problems can be optimized further using iterative only. Like some problems are very easily optimizable using iterative, and with recursive it will be very difficult. So that's why we will learn both. But first we'll focus only on recursive codes. Like we would be using the same strategy, that we would build a recursion, right? For any problem, our flow would be think about what to keep in states, so that given that state, some maximum, minimum, count, some answer is fixed. Okay, so we fix what we keep in states, what do we keep as the value of dp, and how do we calculate that value of some I comma x using the previous states. That's the only thing that we need to decide in any problem, and based on that we will be able to calculate the answers for all the states. Okay, so the main like bottleneck in most of the cases as you go ahead would be like thinking about the states, like what do we keep in the state. Once you like, mostly finding state and transitions come coupled. Like once you like, you think transition and state together, so that like, okay, if this is a state, I can do this transition and it will work, something like that. So you think about both of them together so that it fits in time complexity. But this is the most bottleneck part. Like for easier problems that might not be, because like you already know the state, or it's trivial to think about the state. But in like harder problems which comes in most of the places, states are not very trivial. Okay, so you need to think about that, or you need to at least know a large vocab of states so that you can think across them that okay, this might be a good pick for this problem. Okay, so for this session we would be, first of all, for the first two sessions we'd be building the vocab of state, that what are different states that are possible that you should be thinking in a different problems. Okay, so we'd be taking up examples and we would be learning new and new states that are possible and what you should be thinking any problem when you see them. Okay, so this basically like this also makes your recursion strong, because you will understand how, what all parameters do you should keep in the recursion so that your recursion will work, right? Make sense? So in DP, like in theoretical senses, there are two property that I think some of you might already know, something called overlapping subproblem. Okay, this is some theoretical stuff, but still overlapping subproblem and optimal substructure. So I'll just quickly tell what these terms mean, because if you maybe refer to some other like external source, you might see these terms. So optimal substructure would mean like the optimal value of this dp depends upon the optimal value of this state depends upon the optimal value of this state, and not on any value of this state. Okay, if you know the optimal value of this state, you can calculate the optimal value of this state, right? So this optimal might not be just one single value, it might be two or three values as well. That's perfectly possible, but it's just whatever you want to calculate for this state should be constructible from the same type of values from this state, right? This is one particular notion that is important in like having dp for. The other thing is optimal substructure, that same type of states occur in the smaller versions as well, like I comma x and this I minus 1x. So this is a smaller version of this state, this kind of state, right? So same type of state is overlapping, and like this type, like when you say overlapping, that basically means that okay, there are two states which need the same value. So instead of calculating this twice, we can just save this and reuse it both the cases, right? So that's where it helps. Okay, so this was just some quick brush up on the concepts and theory part. Let's quickly move on to what we can do with dp. So let's start with a very simple problem. Let's say you are given a number n. Okay, and this will be something like 4. Let's say you're given some number 4, and you need to find the number of ways in which you can write 4 as sum of natural numbers. Okay, 1 plus 1 plus 1 plus 1, you can write something like this. You can write as 1 plus 1 plus 2. Okay, I can write it as 3 plus 1. I can write it as 2 plus 2. I can write it as just 4. Right, this is let's say not just 4, I'm not taking into consideration the 4. Let's take 4. Okay, so these are the only 5 ways in which you can write. I'm not considering the permutations of the sums. Like what I mean to say is 1 plus 2 is same as 2 plus 1. I don't consider permutation into account. Okay, and these are the 5 ways in which you can write 4 as sum of natural numbers, right? If you don't consider permutation. Make sense? So now, given this constraint that you don't consider permutations, find the number of ways a given number n can be represented as sum of natural numbers. Okay. Is the question clear to everyone? So like in case 3 is given, the number of ways would be 1 plus 1 plus 1, 1 plus 2, and 3, right? With no other ways. Is this clear to everyone? Is the question clear to everyone? That find out the number of ways in which you can find out a number to be sum of natural numbers. Can I have a click +1 if this is clear? Because think about this problem a bit and think about how you can like keep a recursion. Don't write the answer right away. Just think about it for a minute and then maybe you can write the answer. Because if you're writing, make sure you're not writing the wrong answer. Because if you once you think that my recursion is recursion is good and it is working, you will write it and then you will realize that it is not working. It's rather think about the recursion and whether it will work for the like things that I'm like it will work on all case, and then maybe like tell that okay, this state will work in this problem. Okay. So in particular, this particular number that we're going to count is a special number called partition number. Okay, number of way to partition. This is a special number partition. Think about this one. I'll give you 1 minute to think because this is important. What do we keep in the recursion parameter so that it works? That's it. Just think about states. What do we store, and how can we design, like what is the recurrence by which we can calculate the states? These are the 3 things that you will have to think in any problem. Okay. Don't need to think about how we will implement it or how we will do things here and there. That's something that we will take up later. First, we need to build up the state thinking part. So what can we keep as the DP states and answers? Anyone having any idea? Okay, Tejas. So when you're thinking about DP problems, you need to like write something in terms of like recursion. So we talked about this, right? Whenever like you want to answer something, just return like write in this form that you want to keep DP of some like variable 1, variable 2. Just make sure the names are like understandable. Like I think Saurabh has is decent enough. Like that's somewhat what you need to write. Okay. DP of n comma last taken. Yeah. That this type of states is recurrence of n, DP of n, this type of like write in this format. Okay, current sum and sum to reach, that's not like exact way to write DP. Okay, so write this state, and then if I ask you, then write the transitions. Okay, you don't need to write transitions, just think about the states and what to keep in the value. That's first. If that's wrong, then I think transition will anyways be wrong. Okay, now Abhijit and Amisha I think are suggesting almost the same thing for k equal to DP of no, that's so what are we doing across all keys, Amisha? I'm not sure. Like it's just one breakdown that you have shown, right? Like sum over all k or something like that. Like summation over all k. Yeah. Okay. Sum over recurrence 0, 1, 1. Okay, that's also good. I think okay. So I think the only correct answer will be given by the state like DP recurrence that Saurabh has written. Rest everything will not give you the correct results. Why? Let me explain that. And that's the main importance of building the states correctly. So let me think in these terms that let's say we want to find the answer of 4, right? So in most of the ways, like let's say with Abhijit's one or like Amisha's one, whichever way in which you're taking, like you want to decompose it in 2 values, right? So we can break. So one idea might be we can break 4 into 2 parts. Let's say I take immediate. So I think Amisha was decomposing it into k and like k and n minus k, which will lead to a lot of repetition. I would suggest. Let me take this one that Abhijit was suggesting, and in fact that will be repetitive itself. N minus k. Okay, this is one. So now when we are breaking this into two parts, first of all, we are no longer having a control on the permutation constraint that we put up, right? That like same permutations are considered same. So what will eventually happen is, like if you have 4, let's say the last number you took was 1, okay, and then you are left with 3, and then in 3 you are counting these two ways separately, 1 2, okay, you are counting this one in 3, how to a way to break 3, okay. Then again consider this particular part that you took 2 at the end, okay, and then you wanted to find out the dp of 2, and for 2 you took this particular part, like this particular breakdown of the number, right? You will be counting this particular way in 2, right? For 2 you will count this particular breakdown of 2, for 3 you will count this particular breakdown of 3, and these two paths will definitely be taken in the recursion, like these two like configuration will be counted in both the Abhijit's answer and the Amisha's answer, right? Whenever you have only one parameter in the recursion, these two will definitely get counted. And what will eventually happen is this, in fact, if you think about it, these are not correct, right? These are like same answers, like this should not be considered separate. These are same answers, like we don't want to consider permutations. These are both one answer, right? Make sense? So this is just one answer, and that's why if you just want to break n with no track of what we have taken till now and just want to break it into two parts, the way how do we decide on what has been taken in this and what has been taken in this, and we are not considering the permutations, that part will become very difficult, okay. So that's why keeping just one n in the recursion parameter would not help, okay. So it's very direct to think about this problem, like I can keep the recursion parameter as the n, but the thing is this constraint of having no permutation makes it difficult because we will be over counting in that case, right? If you run this, if you run the if you try to run the code, you will see that you are getting higher values compared to what we actually have. We have only 5, right? Okay, so how do we restrict this kind of permutation? So one thing we can observe in this kind of setting is, for every type of summation that we are generating, if we generate them in a sorted order, the generation is unique, right? Like if we generate them in a sorted order, like 1 1 1 1, or we generate in 1 1 1 2, or we generate it in 1 3 or 2 2, something like this, like if we generate it in a sorted fashion, it will always be every permutation will be counted once. If we count every sorted permutation once, every different summation that can be generated will be counted only once, right? Is this clear? That every if we generate the sequences in a sorted fashion, the permutations will be counted only once, because permutation can happen only once, right? Like there is only one alignment of a permutation. Is this clear to everyone that permutations will be counted only once? Okay, so what we can do is we can keep some sort of dp of, let's say, I comma, like what is the last, let's say, what is the last taken, that what is the last variable that we took, okay, what is the last value that we took, okay, last taken, okay. And let's say we want, so this is nothing but we want to create a value of I, okay, with, let me define this first. Like this particular part will mean we want to create I value with, like there was for some n, okay, out of this we took around n minus k out, like we have considered n minus I out, and now we are left with I, okay, we are left with I elements, and the last element that we took, like last element, like last chunk of elements, like 3 4 whatever value we took, is the taken one, okay. So this value is taken, okay. Make sense? So in this variable is taken, okay. So now next value, like next number that we can take in the sequence, can either be taken or more than taken, right? It can be either of them, because we know that we are generating this thing in a sorted fashion, okay. So I'm doing this for the last I elements. You can also solve this for first, like for the first I elements. That's also a different way. So in DP problems, you might have different styles of implementation where you have, just a second. Okay. So in DP problems, you might have different implementation based on what you keep in DP states. So I'm considering that last I states are left and last I number is left, and n minus I we have taken in some form. Like let's say for 4, let's say if this was n was 4, we have taken 1 and 1, and now we are left with how to decompose 2. Like we are left with two value, and we want to decompose 2 value, and we are left with options. Okay, take for 2 last value is 1, so we can use 1 over here or anything more than 1 because we are generating it in a sorted fashion, right? So now for this 2, how do we design the transitions? So either we can we can either take anything more than taken, right? So we will just have all possible transitions that we can do. Like we can go to